application 1 and 2. So let me get over there and let's go over your questions first, your concept review, so we can go ahead and get those out of the way. Alright, number 3 and 4. Explain the relationship of Charles' law to absolute zero. So remember, Charles' law has to do with volume and temperature. So absolute zero, or using the absolute temperature scale, so that way it mathematically works out with your proportions. Where if you have, say, the temperature doubles, then your volume should also double. And that works with an absolute scale. With the Celsius scale, it doesn't work out right mathematically. So that's how come an ideal gas is supposed to be used, an ideal gas with Charles' law is supposed to be used with the absolute scale or the Kelvin scale. Now remember, with absolute zero is what it's asking specifically about. So remember, at absolute zero, if there's supposed to be the coldest possible temperature or zero temperature, you're also theoretically supposed to have zero volume. In real life, we don't see this, but that's what's supposed to happen. Alright, in chemistry, what is meant by the term STP? What does that stand for? Standard temperature and pressure. So remember, that's at 0 degrees Celsius or 273.15 Kelvin and at 1 ATM. So it has that reference point of 0 Celsius, remember, in Kelvin, 273.15, and then it's 1 atmosphere or 1 ATM. Alright, number 3 and 4, sorry, 1 and 2 now for the application. Alright, what would happen to the balloon's volume if the pressure were doubled? So remember, pressure and volume are inversely proportional. So if one goes up, the other goes down. So if the pressure is doubled, then the volume should go down. It should be cut in half, technically. So hopefully you got that exact answer. And then it says, what if the pressure was quadrupled? So that means that if it was 4 times that, then that means it should be 1/4 its original volume. So basically, whatever one happens, it has to be the opposite in equal amounts. So if it's doubled, then it's half. If it's quadrupled, then it's 1/4 of its original volume. Alright, number 2, sperm whales are the deepest diving wells known. When a sperm whale dies from the surface to great depths, the air in its lung progressively shrink until the lungs are completely collapsed. That's a bummer for us. For them, it's supposed to work. When the whale ascends, its lungs return to their former size. Use Boyle's law to explain this phenomenon. Okay, so what's happening? So if it's going deeper down in the ocean, is the pressure increasing or decreasing? Hopefully you said increasing because it's going deeper in the ocean. So what should happen to the volume on the inside of its lungs? Should it go up or should it go down? It should go down. That's the reason why for it. So the deeper the whale descends, the greater the water pressure. As the pressure increases, the volume must decrease. Now, whenever the whale goes back up to the surface, is the pressure going up or going down? If it's going back up to the surface. Right, it should go down. So what should happen to the volume then? The volume should go back up. So that's the second part of it. So as the water pressure decreases whenever the whale goes back up, you should have, whenever the pressure decreases, I'm pointing the wrong direction. As the whale's going up, the pressure is decreasing. That means the volume should increase. Alright, I have some classwork for you today, so I'll be kind of helping you thinking and getting back over it. You want to work on page 65, question number 3, that application question. We've done all the other questions, but not that one yet. So you might want to pause the video while you flip over there and try to work out that problem on your own. So a gas sample is connected to a closed-in manometer. The difference in mercury levels in the two arms is 115 millimeters. What is the gas pressure if the atmospheric pressure is 750 with a decimal point torrs? State the answer in both torrs and atmosphere. It should maybe take you about 2 to 3 minutes to solve. Hopefully remembering how to solve these kind of helps jog your memory. So go ahead and pause the video. Give you about 2 to 3 minutes to try to solve this on your own. And then unpause the video and come back. Alright, so you will notice that it says that this is connected to a closed-in manometer. So if it is closed or if it is not connected to the atmosphere, do we care what the atmospheric pressure even is? No, we do not. So it gave you what the atmospheric pressure is just to check to make sure and that you knew what you were talking about, but we don't care what the atmospheric pressure is. You're just checking to see, okay, if it's closed, how much does it move or how much does it shift by? So if it moved 115 millimeters, then that means in torrs it should be what? 150 torrs. Sorry, 115. I cannot talk. 115 torrs. If it was 115 millimeters of mercury, then it should be 115 torrs. Now, it wants it also in atmosphere. So if you're going from torrs to atmospheres, think of it this way. How many torrs or millimeters of mercury are in an atmosphere? 760. Do I have 760? No, so I need to at least divide by 760, 150 by 760. That'll give me in your calculator 1.1513. So this is a division problem. It says that for this one, this is a unit. So there's 760 torrs in a millimeter of mercury. So because of that, you don't have to worry about this one for sig figs because this is a defined value. This one has 3 sig figs. So what should your answer have? 3 sig figs. So 0.151 and then atmosphere. So that's the answer for the atmosphere part. Here's the answer for the torr part. So hopefully this kind of helped jog your memory to think, okay, here's what's happening with a manometer. All right, let's go back and let's review a little bit. So take out a piece of paper so we can write down terms and definitions you don't know. I haven't made you copyable terms like I have in some of my other classes, but you need to learn your terms and definitions plus just the math part. So thinking back over it, what do you call the, well, do this way. There are 5 parts to the kinetic theory of matter. I haven't made you write them out yet, but you need to be able to know them. So what's one part of the kinetic theory of matter? Gas molecules are in constant motion. What's another one? What's the second part? Gas molecules undergo elastic collisions. What's the third part? The energy of the gas molecule is related directly to temperature. What's the fourth part? They have the gas molecules are very far apart and are negligible in volume to the volume of the gas. So we're talking about the volume of the gas, I mean the whole gas, not an individual little atom or molecule. What's the fifth part? Gas molecules have negligible attraction between them. So they might have a very slight attraction, but basically if you're talking about the whole gas, not at all. Alright, what do you call the property for gases that means for gases to be able to be mixed? It starts with an M. Miscible. That's on page 60 and right underneath the hot air balloons. If you didn't mark it earlier, mark it today. What do you call the ability of gases to mix by random molecular motion? Diffuse. Go ahead and mark that as well. Alright. So, talking about the equations that you need to know. Alright, what is the equation for kinetic energy? I'm going to go ahead and erase the classwork so I can use this part of my board. Alright, equation for kinetic energy. What is it? Alright, good. 1/2 mv squared. What's the equation for pressure? Pressure equals force over area. Good. What is the SI unit for pressure? Pascal. Perfect. Alright, what is the device that's used to measure atmospheric pressure? Barometer. Who discovered atmospheric pressure? Or who discovered that it could be weight or air has weight? He invented the barometer. Evangelista Torricelli. Good job. Make a note, first and last name. Let's see. What do you call the barometer that doesn't use air? It's a flexible box. Where mercury barometers are too dangerous for the average person. Aneroid barometer. Alright, if I have, we're just going to make something up, 1,120 millimeters of mercury, how many torrs do I have? 1,120, because the torr and the mercury, millimeters of mercury are equal. I did not work this out ahead of time. So if I have 1,120 torr and millimeters of mercury, how many atmospheres do I have? I'm going to have to type this in because I did not work this out. Alright, so remember, torrs and millimeters of mercury, there are 760 of them in 1 atm. So if I have 1,120 torrs, how many atm, how much in atmospheres is that? So you take 1,120 divided by 760, that gives you 1.47, I'm just going to round. This is not proper sig figs, I'm just rounding it for you. So this would be atm. This is fast. Technically it should have 3 sig figs, so 3 sig figs. It's going to bother me about this. Alright, so that would be the answer for that. So just make sure that you know all those conversions for it. Alright, what is standard atmosphere or standard pressure? What is that? So if I'm talking about standard atmosphere or standard pressure, how many ATMs do I have? 1. How many torr or millimeters of mercury? 760. Good job. Alright, what do you call the device that's used to measure the pressure of a gas? Manometer. Great job. What if, I probably shouldn't have erased that. What if it's open to the atmosphere? What do I do if the So let's say the atmosphere is 764. Now, let's say the millimeters of mercury on the inside of the manometer has shifted, we'll say 23 millimeters of mercury to the right, or it's higher on the atmospheric side. Which one's stronger? The gas or the atmosphere, if the mercury is higher on the atmospheric side? Alright, that means the gas is stronger because the gas is winning. Do I add or do I subtract the 23 then? Right, I add. So this would be 783 torr for this particular example. Let's say though that it shifted 23 degrees millimeters of mercury towards the gas. Which one's stronger? Atmosphere. So do I add or do I subtract? Subtract. Good job. So fast math. 723. I don't trust my ability to do fast math very well on the board, so just so I don't want to be wrong. Okay, good. 737. I was right. I should trust myself more. Alright, so that'll be the answer for this one if it's shifting towards the gas side. Alright, remember a closed-in manometer, we don't care what the atmospheric pressure is because it's closed on the inside. So if it's a closed manometer, then if it shifts 23 degrees millimeters of mercury, then that means it has a pressure of 23 torr. So those are pretty straightforward. Okay, thinking about it with the gas laws, what does Boyle's law say? Boyle's law says that pressure and volume are inversely proportional. So make a note of that. At a constant temperature, the pressure and volume of a gas are inversely proportional. Alright, what does Charles' law say? Charles' law says that at a constant pressure, that temperature and volume are directly proportional. So what happens to one, must happen to the other. Alright, we looked at this equation yesterday that kind of ran out of time, but I introduced it earlier. What is the equation for the combined gas law? You can use it to solve combined law problems. You can also use it to solve Charles' law and Boyle's law. So rather than memorizing 3 separate equations, you just memorize one. So what is the combined gas law? I'm going to need this a lot today. P1 times V1 over T1 equals P2 times V2 over T2. This is the combined gas law. Boyle's law is in the top part, and Charles' law is off to the side. You might remember that the P over T part is a Montan's law from physical science. You don't have to know that this year. I'm just pointing out in case you were still wondering about it. Alright, so let's see. What temperature scale do you have to use if you're going to use Charles' law, or if you're going to use any type of temperature changes? Right, you have to use the Kelvin scale. So if you're given to it in Celsius, you gotta convert. How do you go from Celsius to Kelvin? You add 273.15 to it. Alright, that's pretty much everything we've talked about so far. So if you didn't understand some of that, or if you need help, be sure to email me. But also, go back and watch part of it if you need help going over the terms again. So make sure you are studying. Alright, let's go over on page 68, the combined gas law, volume, pressure, and temperature. So this is the combined gas law. We're going to use this a lot today. So your book points out, when solving problems using the gas laws, only the initial and final conditions matter. It doesn't care how long it takes. You just look to see, what do I start with? What do I end with? So your book points out that in a lot of cases, scientists, they want to use what's a standard, or kind of like what's a reference point for them. So the standard temperature and pressure, often at STP, kind of say, okay, here's that standard temperature and pressure, and then how much did the gas change by? It's kind of like a reference point. So standard temperature and pressure, abbreviated STP, this is at 0 degrees Celsius, or 273.15 Kelvin, and it's 1 ATM, or 760 torr. Your book points out, even though technically you're supposed to add 273.15 to these calculations, for convenience sake, your book is going to just leave it at 273. Now, whenever I work out my calculations, I type it in as normal. That's probably the reasons why that I leave it in personally, so that way I want to make sure I get the full exact answer. And typically that 0.15 doesn't matter, to where it doesn't really even cause a change with significant figures. It doesn't affect it at the end. So if you are using the full version, 273.15, be sure to write it out so that way I can tell if you make a mistake somewhere that it's not because you rounded wrong. So that way I can check and give you full credit for your exam or for any quizzes coming up. So your book points out they ran on to 273. I personally don't like that because they're just being lazy in my opinion. So I like to keep it the full version. But you'll notice once we get to the end, it doesn't affect the final answer. So keeping on that point 15 doesn't really matter. The book just got tired of typing in 273.15. So they just rounded for convenience sake. I don't like to do that. So that's the reason why I don't do it. Alright, so let's practice first off with using the combined gas law. What I recommend doing to solve these is you want to write off, okay, what am I starting off with? This makes it easier to figure out what are you looking for and how to set it up. So I like to write off all 6 parts, P1, P2, V1, V2, temperature 1, temperature 2. It does matter that you put them in the proper spot. So you want to look and put all of your initial conditions together and then all of your final conditions together. So it does matter, you can't just stick them in wherever you want. You have to make sure that you put them in correctly, because if you stick them in the wrong spot, you either multiply or divide incorrectly. That's the reason why you gotta be careful. Alright, so a sample of methane gas occupies 5 liters at 730 torrs and 27 degrees Celsius. What volume will it occupy at 1 atm when cooled to the temperature of dry ice, negative 78 degrees Celsius? Alright, what am I starting off with? Let's find those first things first. Alright, so a sample of methane gas occupies 5 liters, or if it's liters, liters is the unit for what property? Volume, so this has to be volume. So for this first one, I should have left more space. I'm going to go ahead and move it so it won't bother me the whole class period. Get it right over here so I have plenty of room. Alright, so 5.00 liters, so that is not in the right spot. 5.00 liters for volume, so I have my first volume written. Alright, at 730 torr, but 730 torr, what property is that? That's got to be pressure, so 730 torr. And a temperature of 27 degrees Celsius, so I got to fix it. 27 degrees Celsius at 273.15 comes to what? 300.15. Again, I leave it on because I want to get an exact answer. Your book rounds just for convenience sake. I'm going to leave it on. It's not going to mess up my final answer. Alright, so these are all my starting conditions. Alright, now let's see what it gives me, what's changed. What volume will it occupy at 1 atm or 760 torr? Since this one's in torr, we want to keep the other one in torr. So because I don't want to have to convert. So it says for this one, 760 torr. And then it says when it's cooled to the temperature of dry ice, negative 78 degrees Celsius. So negative 78 degrees Celsius added to 273.15 becomes what? 195.15. Alright, so it's asked me what volume will it occupy. So this is what I'm finding. I'm finding volume number 2. So I have all my other variables now, so I can just plug them into the correct spot. So I'm just going to write it off over here, off to the side. I'm going to shift over a little bit so you can see it a little bit better. So I'm just going to fill them in, taking that equation and just putting it over here. I'm probably going to leave off units so it'll fit a little bit better. So 730 for the torr, 5 for the liters, 300.15. I always run out of space. Alright, so the second pressure, 760 torr. I'm finding that second volume. The temperature, 195.15. Alright, I gotta get the second volume by itself. How do I do that? Alright, well I gotta cancel these out. I can move this one over here into the numerator spot. So that'll cancel out this one, then I divide by this one. And that'll cancel out that. So that'll give me V2 by itself. So you do have to type it in your calculator with order of operations, it doesn't matter, but it does matter if you're multiplying or dividing, so you have to be careful. So you multiply 195.15 times 730 times 5, you want to do the whole top together, and then divide by 760 and divide by 300.15. So just be careful though that if you go down here, you don't want to press divide by 760 times 300. You're taking your entire product of the top and divide by the entire bottom. So you're saying 195.15 times 730 times 5 divided by 760, and then still divided by 300.15. The answer for this one comes to 3.1226, and that just keeps going. So even though we left on that 0.15, it's not going to mess up our final answer, because our final answer should have how many sig figs this is multiplying and dividing. Take a look up the decimal point for this one. Yeah, I did. Alright, so 3 sig figs, 3 sig figs, 5 sig figs, technically. 3 sig figs, 5 sig figs. Alright, so how many should our answer have? 3. So 3.12, and that's the final volume. So this one's in liters, this one must also be in liters. So that's where that answer comes from. So this isn't necessarily difficult math, it's just multiplying and dividing, but you gotta know how to set it up, and that's where it starts to get tricky. Alright, we're gonna practice a little bit more with this. My projector turned off, and I've got to turn it back on, so I'll have to wait for it to load. But we're gonna practice with this. So, whenever I put up the first two problems, I'm not gonna wait that long for you to solve them, because you can pause the video and then come back to it. So, you probably want to spend about 5 to 10 minutes trying to solve them on your own. If you get completely stuck, you can unpause the video, watch me explain part of it, and then try to solve it on your own, because you need to know how to do this. So that way it'll help you for future quizzes and then also for your exam next week. Alright, let me get up those practice problems. All my stuff shifts around whenever I plug it in. Okay. Let's see. I made the font bigger yesterday, so I hope it'll be a little bit easier to see. Okay. I think that shows up on the video better. No, this is the wrong thing. Sorry. Don't save. Give me a second. Okay, here's the proper one. Alright, so I think that shows up in the slide. Let me double check to make sure that this fits well. I tried to fit the whole thing in the PowerPoint. Okay, I'm going to read it out loud. If you're trying to read it off the cell phone, I don't know how well it'll show up, so I'll read it slowly, and then you can go back and rewind it if you need to for it. Alright, so if you compress 1,500 liters, with no decimal point, so 1,500 liters of nitrogen at an initial pressure of 1 with 2 zeros and a decimal point, ATM, until the pressure reaches 450 ATM, with no decimal point at that one, what will the new volume be? So you're assuming temperature is constant. So again, I'll read it again in case you can't read it very well on your screen. If you compress 150 liters of nitrogen at an initial pressure of 1 ATM until the pressure reaches 450 ATM, what will the new volume of the gas be? So assume temperature is constant. Letter 2, I'm going to go ahead and read it so you can work on both of them at the same time. Let's say you have a balloon of 2.50 liters at a temperature of 25 degrees Celsius. If you heat the balloon to a temperature of 50 degrees Celsius, what will the new volume be? I'll help you with sig figs as we go over the answers, so I'm not going to try to read those out loud. So let's say you have a balloon of 2.5 liters at a temperature of 25 degrees Celsius. If you heat the balloon to a temperature of 50 degrees Celsius, what will the new volume be? Assume pressure is constant. So go ahead and pause the video, try to work them out as best you can on your own, and then come back. But if you get stuck, unpause the video so you can see me explain it. Alright, so this first problem, if temperature is constant as a side note, and we're talking about changing pressure and volume, what law are we using? Boyle's law. So, because of that, if the temperature is not changing, I can basically cancel out those parts, or the bottom part, and just work with the top part of my equation. So even though I'm using one equation, these bottom parts, it doesn't matter right now, because they're not changing, they're the same on either side. So this is just Boyle's law, but you want to work it with the combined gas law. So it's 1 ATM. So if you're finding out on the right over here, so you can just see it. So 1 ATM is my starting pressure. So initial pressure of 1 ATM, and it has 1,500 liters. So 1,500 liters, no decimal point. The second pressure is 450 ATM, and I'm asked what the second volume will be, so I'm finding that again. Alright, so plugging that into my equation. So 1 ATM times 1,500 liters. The pressure is increased to 450 ATM. What is my second volume? I don't have to worry about the bottom parts because it's not changing. So I can just skip the entire bottom part for it. So 1 times 1,500 to get the volume number 2 by itself. I divide to cancel it out. And that gives me volume 2 by itself over here. So 1 times 1,500 divided by 450 gives you what? Hopefully you found 3.3333, and that just keeps going for forever. Alright, so the first pressure has 3 sig figs. The first volume has 2 sig figs. The second pressure has 2 sig figs. Now, so as you're multiplying and dividing, you go off number, you go off by place. By number. Good. So this just becomes 3.3. This is liters for volume. That means my second volume has to be liters as well, because they have to be equal. Alright, so that's how you solve that first one. So let's go over the second one, because you should have attempted that one by yourself already. If you want to go ahead and attempt it by yourself, you got completely stuck on the first one, then pause the video and try it. Alright, let's say you have a balloon of 2.5 liters at a temperature of 25 degrees Celsius. If you heat the balloon to a temperature of 50 degrees Celsius, what is the new volume? Assume pressure is constant. So if pressure is constant and not changing, do I have to worry about it? Nope. So those just get X'd out because they're not important right now. So what law is this if I'm talking about a changing pressure, a changing volume and temperature? Charles' law. Good job. So let's figure out though what I am finding. This is V2, I just noticed that, and T2. So first volume and the first temperature. Alright, so let's plug in what I'm started off with. So I have a volume of 2.5 liters, so that's my first volume. At a temperature of 25 degrees Celsius. Can I use Celsius though? Nope. So adding 25 to 273 degrees Celsius, that gives me 290. Oh, I'm looking at the wrong column, sorry. I'm looking at 298.15. Alright. Why? Okay, so looking at the second problem, it's asking me what's the second volume if the temperature is increased to 50. I need to move my mouse more, that's my problem. So this first temperature is 298.15, so 273.50, this becomes 323.15 per Kelvin. Alright, how do I solve this? Well, I don't have to, I wrote that in the wrong spot. 323.15. I got distracted with my changing slide. So I'm finding the pressure. Alright, so plugging this in, I can just ignore the entire pressure part and just cancel that out. So my first volume is 2.5 milliwatt units. My first temperature, 298.15. My second temperature, 323.15. I'm finding my second volume. Alright, how do I get volume by itself? Right, I multiply. So 323.15. I'll cancel out. So multiply these two numbers together and divide the product by 293.15, and that'll give you your answer. For this one, the answer comes to 2.7096, and it keeps going. So looking at sig figs, so 2.5, that's 2 sig figs. 323.15, 5 sig figs. 298.15, 5 sig figs. But since this one has 2, this answer must also have 2. So 2.7, since this is liters, that must also, your answer must also be liters as well. So that's the answer for number 2. Alright, let's go on to now and practice with 3 and 4. Okay. So again, pause the video if you need to see the whole thing so it'll help you out for it. I'm erasing this so I can have a clean board. So again, these are a little bit more complicated, but you need to have the practice with them. Alright, let's say, I'm reading number 4. A child at a country fair has let go of his toy balloon. If the initial volume of the balloon was 2.5 liters, the atmospheric pressure is 1 atm, the temperature of the fairground is 25 degrees Celsius. What will the final volume of the balloon be when it reaches an altitude where the air pressure is 0.25 atm and the temperature is negative 15 degrees Celsius? Remember, the higher the atmosphere you go, the colder it gets, and there's less pressure, so that's why that changes. Alright, so again, if you see a question like this and it starts to look a little bit overwhelming, just write down what you know to help you start it. If you want to solve these on your own as a side note, go ahead and pause it and try to solve them, but be sure to come back as I walk through them. Alright, so just write down what you know for it. Alright, so starting off, it says, the Child of the Country Fair has Lego Vista balloon. The initial volume of the balloon was 2.5 liters. So 2.5 liters, that's my starting volume. I'm just going to leave the zero so I won't forget. The atmospheric pressure is 1 atm. And the temperature of the fairground is 25 degrees Celsius. Remember, I can't use Celsius, so add 273.15 to it. I get 298.15. So that's for the temperature in Kelvin. Alright, it says, what will the final volume of the balloon be? So it's asking about volume, so I already know that's what I'm finding. When it reaches an altitude where the air pressure is 0.25 atm, and the temperature is negative 15 degrees Celsius. So add negative 15 degrees Celsius to 273. That'll give me 258.15 Kelvin. So again, once you plug everything in, it's not as scary. So make sure that you write down probably a list like this. So it'll help you see, okay, what are the parts that I have, so that you can just plug them into your equation. I'm going to come over here so I have enough space. I never have enough space. Alright, pressure number 1. So I'm going to leave off units so I have space. So pressure 1 atm, my first volume, 2.50, my first temperature, 298.15. Those are all my starting conditions. Alright, my second pressure, 0.25, finding second volume, second temperature, 258.15. So that's everything plugged into the proper spot. Alright, how do I get second volume by itself? I'm trying to make sure there's a bar in the middle of it. No, I think you can see it. I should show it. Nope, wrong direction. Okay, that's a little bit easier. Alright, so how do I get volume 2 by itself? So to cancel the bottom, I multiply. So 258.15. That'll cancel out the bottom. Now I gotta get rid of this 0.5. What do? Divide. Alright, so I'll cancel out that. Alright, so again, the entire top is multiplied together, and then you divide by the entire bottom. So be careful that it's this number times this number times this number divided by this number divided by that number, because you got to get the entire top divided by the entire bottom. Alright, so pause if you're not ready, try to solve for this. Alright, so assuming that you did that, you'll notice that your second volume is 8.6583, and then it just keeps going. Alright, significant figures. Looking at this, how many significant figures should my answer have? Well, because this one has 2 sig figs in the second pressure, that means my answer should have 2 sig figs as well. So this becomes 8.7. Since I'm in volume, this one is in liters, so that means your answer must be as liters as well. Your volume is not always liters as a side note. It typically is, but not all the time. So that's the answer for number 3, 8.7 liters. Number 4 is basically the same idea, so that way you can have practice with that one. So go ahead and try to solve it on your own if you haven't tried already. Alright, so let's go through that one. Alright, let's say some scientists go deep sea exploring in a giant transparent balloon because they're weird. If they start their voyage in a balloon with a pressure of 1 atm, a temperature of 20 degrees Celsius, and a volume of 5,000 liters, what will be the pressure inside the balloon when they reach the depth of the temperature of the balloon is 2 degrees Celsius? Why? And the balloon's volume is 1,170. I need to remember to move my mouse. That's the reason why. My computer shuts down after about 5 to 10 minutes or starts to go to sleep. So I just need to remember to move it. Alright, so what's my starting conditions? Alright, so looking at that one, they are starting the voyage with a balloon with a pressure of 1 atm. So 1 atm. And they have a temperature of 20 degrees Celsius. 20 degrees Celsius becomes 293.15 in Kelvin, 293. So my first volume is 5,000 liters. Is there a decimal point? Should I put a decimal point? Yep, I did. Figured I did. Alright, so what am I finding? What will the pressure be inside the balloon when they reach a depth where the temperature of the balloon is 2 degrees Celsius? So 275, I'm writing that in volume, 275.15, 273 plus 2. And the volume is 1,170 liters. So I'm finding what the second pressure will be. So again, once I write out everything, I just fill it into the proper spot. Alright, so plugging in everything correctly, it's 1 ATM times 5,000 liters over 293.15 for temperature. We don't know what the second pressure is. My volume is 1,170. My second temperature, 275.15. Alright, how do I get rid of the 275.15? Can't see me, but it's okay, you can still hear me. Right, you multiply 275.15. That'll cancel out that. Alright, how do I get rid of the 1,170 volume? 1,170 gets divided. Alright, so again, just plug it in and solve. So that should give you your final answer. So go ahead and pause and do that if you didn't do so already. Alright, the answer for the second pressure is 4.0111, and then I got tired of it. So 4.011. Now, based on your sig figs, this has 3, this has 4. Sorry, that has 4. The temperature has 5. You don't know what the second pressure is. This one has 4. This one has 5. So this one has the smallest number. So when multiplying and dividing, that's how many sig figs your answer should have. So for this one, 4.01. This is pressure. So since this one's an ATM, the second pressure must also be an ATM. Alright, so that is the final answer for those practice problems. Alright, so hopefully that'll give you some good practice so that way you feel comfortable doing these. If you have questions about it or if you're confused over how do you solve these, be sure to email me and be sure to ask me. I'm more than happy to have a Zoom session or something like that with you. So we can help you to be able to be confident in your math. Alright. Okay, let's introduce. No, it probably took you a while to work that math on your own, so I'll go ahead and I'll let you go. So we're going to have to talk quick tomorrow in order to cover all of your terms for it. So just make sure you're paying attention tomorrow. Alright, your homework for tonight. Read pages 71 through, you can go ahead and read it. So 71 through pages 74, 71 through 74. Answer on page number 75. Answer questions 1 and 2 on page 75, the concept reviews. So concept reviews 1 and 2. You're also going to do on page 76 as a practice. You're going to do problem number 3 on page 76. So number 3 on page 76. We'll just do just one for today. So on page 76, question number 3. Alright, so again, all together, read pages 71 through 74. Enter the concept review 1 and 2 on page 75. On page 76, do problem number 3. And that'll be it for tonight, but you definitely want to practice this more. So if you have any questions, you should ask me, because your homework tomorrow will be more practice with this. Alright, you have a good night.